Hello, my name is Stuart Williams. I'm from the University of Louisville, and today I'm going to talk to you about electrothermal flow. This is something that our lab runs into a lot when we look at microfluidic devices, specifically those that use dielectrophoresis or other AC electric fields. So this video just gives you an introduction on what it is, how to identify it, as well as some other aspects of electrothermal flow. So today what I'm going to talk about is the basic theory, as well as looking over how one would go about doing heating and temperature field calculations and estimations. We'll get into numerical modeling in more detail, and also how to conduct some of these measurements. Now, today's video is going to be brief, but there is literature out there. There is some textbooks as well as journal articles and review articles that you can reference. But in the end, many times, significant electrothermal flow will be present in dielectrophoretic systems. And this is especially true if you're going to have high fluid conductivity media, so biological growth media, etc. And we'll go over some of those figures and examples in a little bit. So here we're going to provide you the basics to help you identify, understand, and model electrothermal flow. And you have to start with the equation. And that's what we're going to do here. Now, we are not going to go through the derivation. I have some references at the bottom that you can look at for the derivation. There's other resources that also have similar derivations. But the electric forces act on incompressible media. We're going to assume liquid flows through all of this. We are going to ignore any phase components. So if you have more an AC signal that has different phase aspects to it, we're not going to talk about those here, though that information is available in other literature. But we're going to neglect the field complexities. And we're also going to incorporate the body force, which is this expression that I'll go over in a second. We're going to incorporate this body force with the second equation here, the Navier-Stokes equation. So let's go over this electrothermal fluid body force. Now, all forces, I'm going to go down to the equation, Navier-Stokes equation, all forces that act on the fluid body will go here. So this is capital F. So this could be other forces as well. We would throw our electrothermal force in here for the Navier-Stokes equation. So let's go over the equation itself, and we'll talk about some different aspects of it. So first, we have two terms. Term on the left, term on the right. Now, the term on the left is the coulombic force, or derived from the coulombic force, and the one on the right is a dielectric force. Now, typically, the force on the left dominates. It's on the order of 10 to 11 times greater than the one on the right, than the dielectric force, but that's if you have low and I'm going to put this in quotes because I'm going to define this in a little bit. If you have low frequencies, that's going to be the case. So let's go ahead and define that and get that out of the way. So what do I mean by low frequencies? Here we have our frequency term, omega, and then right next to it we have our frequency term that goes into tau. So tau in this case, this is a misprint. Let me rephrase this. Sigma over epsilon, where sigma is the fluid conductivity. So tau goes into here, and then omega is the AC frequency, where omega is equal to 2 pi f. So then you go about, and then if your frequency is high, then the denominator here gets high, and then the coulombic term it becomes negligible. So once you are at lower than the relaxation frequency. So the relaxation frequency is that tau term. So if your frequency is greater than that, then that's when the coulombic term starts to become negligible and decreases. And then the dielectric term dominates. And if that's the case, first off, you'll see it could slow down. And then you could also see a reversal of fluid motion. So that's a characteristic here. If you also look at the dielectric term, you also notice that it is not AC frequency dependent, so it's a constant. But in general, this term, the dielectric term, is less than the coulombic term. So we're going to focus a lot on the coulombic term when we study these systems. That being said, we also see that, let's go over some other terms. We have this alpha term and this beta term, which is depending on the fluid that is used. So this is for water, how much permittivity and conductivity change with respect to temperature. Here I have it expressed as an inverse degree Celsius, but you typically see these also expressed as a percentage. So that's one aspect. So just to quickly review, we have that we have to be mindful of the frequency that is used. We also know that this force is due to the gradients or the change in electrical properties. So the change in permittivity and the change in conductivity with temperature. But then the last aspect of this is that it is temperature gradients. So I'm going to take that dot product that's in the numerator of the coulombic term. So this is what's really driving other things, in that it's not how high you heat it, but it's the gradient, how sharp is your change in temperature, not how much are you heating it, not what the magnitude is, but what is that change. So the sharper the temperature gradient, the stronger the electric field. But it's also a dot product. So the temperature field, let's just say the temperature field, or gradient I should say, goes in one direction, and if the electric field is orthogonal to it, then you're going to have strong electrothermal flow. And this is an important aspect, so I'll go over later how you can utilize this to potentially reduce electrothermal flow in your systems. So how to identify electrothermal flow? Typically, they are vortices. You'll see swirling motion. Now, I say that, you can almost say this is the same for all other electrohydrodynamic flow. There's an electrohydrodynamic flow that we're not going to go over, which is AC electroosmosis. We're not going to go over that. That can also cause swirling motion. But you can also think of it as that you have, for these studies, at least they're shown here, they're trying to trap particles, or they have trapped particles, using dielectrophoresis. So for the example on the left, we have an electrode, so a coplanar electrode set. So they're looking at this from the side. You have a coplanar electrode set, and then they have successfully trapped particles using dielectrophoresis. But then they've also noticed that we have this significant, pardon me for that, they have significant electrothermal flow that's swirling within their system as well. And this is a good paper by Nick Green and others for you to look at as well, and I'll reference it a few more times. But either way, it's characterized by this swirling motion. And then here on the right, a study that we did in our lab where we have a probe where we're able to trap particles using positive dielectrophoresis, but then we also noticed that there was significant swirling, hence this electrohydrodynamic, which is derived from electrothermal motion in this case. We know some swirling to accompany this. So when you see this, especially at higher frequencies, so we'll say, depends on the fluid conductivity, but we'll say greater than the tens of kilohertz, especially if you're in higher fluid conductivity media. If you're in low fluid conductivity media, we'll say in the hundreds of kilohertz for low conductivity media. Then this is likely electrothermal fluid motion as opposed to AC electroosmotic motion. So before we get back to electrothermal flow in more detail, we're going to talk about temperature fields and electric fields and how the best way, in my opinion, is to go about just modeling them. Now, we can do some estimations, and we'll talk about that in a second, but it's all based off of the equations that are shown here. So the first equation that is shown here, this is what you can use to solve for the electric field. And I have an example of a 2D space where we'll put this in action. And this is a Laplace equation. So you can use this to solve for the electric field, so it's a rather straightforward calculation. And typically, when we go through when we go through and apply the electric fields with the temperature and then later the fluid dynamics, we're going to ignore convection. And usually you can ignore convection for microfluidic systems because it has a small Peclet number. We will go over some instances where where you should not ignore it, or at least you should be aware of errors that happens under certain circumstances. We'll go over that in a little bit. And then also, since we're typically dealing with an AC electric field, we're going to ignore any heating oscillations that happened, and usually at greater than kilohertz frequencies. Then you can say that this is a steady state heated system. So let's get back to our equations. We have our electric field, which is due to the Laplace equation. And then we have our, to solve for the heat transfer of our system, when we model this, we're going to be using a variation of Poisson's equation, where we have the thermal conductivity of the system, so glass, water, whatever it may be, and then, in this case with water, because our electric field is in the water itself. So here we have fluid conductivity, that's back here, and then we also have the magnitude of the electric field, and then we square that. So that latter term is the source of our heat, and then you can use this equation to solve for our temperature field. So this is an example, pulled it from the reference below, where they used the Laplace equation to solve for the electric field space, and then they solve for the electric field. So let's go over this, and let's talk about this diagram for a second. So within this diagram, we have, and this is looking at from the side, we have a channel of water, and then we have a glass substrate, and then we have a glass lid. Now, I've seen this mistake before, and I do not want you to make this same mistake. If you are going to go about making this system in terms of modeling something and modeling your system, for the thermal solution, you need to include the whole chip. You need to include, maybe it's a glass cover slip, maybe it's a silicon wafer, whatever it may be. When you're solving for temperature, you need to include the whole thermal space. Do not just say the liquid portion. Don't constrict your thermal portion just for that. Now, for the microchannel space, the liquid space, this is where you are going to solve for your fluid dynamics and for your electric field. Now let's go over their boundary conditions for a second. So in this case, they are showing a potential here at the wall to be 0. They have a potential down here to be some positive voltage. And then for the electric potential for the walls, this is an insulative boundary condition. So with those, you can then solve for the electric field. And then when you solve for the electric field, you can then go back and use that and plug that into the remaining portion of the heat transfer equations. So let's go over that for a second. So when you have your thermal space, they say the outside boundaries are are at a set temperature, and then you have a insulative wall here. So in this case, they are not showing it. You're looking at this and say, hey, I only see one electrode. Why is that? This is a think of it as a mirrored boundary condition, because their system, I'm going to draw just the electrode part. So I'm going to draw an electrode here, a small gap, an electrode here, and then where I'm going to have my dashed line, that's their system. Because so due to symmetry, what they're saying is that this is some positive potential, this is some negative potential, and therefore at this boundary, my potential here is going to be 0. So they have that. That's why they can do some symmetry here with respect to the electric field. And that's also why they can do some symmetry with respect to the thermal conditions as well, just due to the mirror image of the system. So they just save some computation time here is what they're doing. So once you then solve for the electric field and then the temperatures, now we can go back to our body force, which this needs temperature gradients, and then it also needs electric field information in order to solve for that. So typically what happens is that you have a simulation space that solves for the electric field, and then it sends that solution into a thermal numerical solution, and then that sends its solution over to a fluid dynamic simulation space. And then this can be coupled, or this can be uncoupled. And then this just depends on you can save computation time with one over the other. And I'll get into what all that means. So this slide helps us talk about, again, the insulating field boundary condition. So this will get back and reiterate that, yes, we need to simulate the whole system. And then if you're trying to solve for say a microchannel, and we'll draw a 2D microchannel similar to what we've done before. So out here, they said that, okay, we're going to have a 300 Kelvin temperature over here. We're going to have a 300 Kelvin temperature over here. But when they did their symmetry, so I'll draw a dashed line here for their symmetry, they said that is their... And let me quickly edit that so it looks a little cleaner. Oops. Pardon me for that. All right. So for that boundary condition, that's the same. That mirror image condition is the same as an insulative boundary condition. So if you have a repeating structure, or you have typically if you have a repeating structure, you want to have this insulative boundary. Otherwise, you want to make sure that you set your temperature boundary conditions appropriately. Now, also one thing I'm going to comment on is how wide should one make this system? Yes, our electrode is here, and what we're interested in is right around here, but how wide should we make our system? So what I was trained on when I went through these simulations, or what I was told, and this is what I pass on, is that we need to look at a length scale of our system. So, or the length scale that is of interest to us. So the length scale that is of interest to us is, I'll say, from the top of the channel to the bottom of the channel, and I'm going to call that L, just for simplicity. So this L, what I'm going to say is that if this channel height is L, and technically you're not going to have a lot of electrothermal over here where I drew the X. There's not going to be a lot of action over there, but you have boundary conditions. You're going to have a temperature boundary condition, and then you're also going to have at least right here, you're going to have a potential boundary condition. And that if this becomes really, really close, if this vertical boundary infringes upon the space that you're interested in, it's going to impact what's going on. So you don't want it close, but you don't want it so far away that your simulation space becomes huge. So what should it be? Now, I would say at a minimum, your width should be about 10 of those characteristic lengths. It'd be better if it was about 20. So if you want to, in that way, it's far enough away, quote unquote, it's far enough away to where that temperature boundary condition and electric field boundary condition shouldn't influence what's going on too much. But, so we'll say if your width, in this case, is approximately the same as your height of your channel, that is definitely going to produce errors. And then another aspect is that I talked earlier about why you should model your whole system. Now, I'm going to talk about why you should model your whole system for the thermal boundary condition. So let's say that this is our electrode, right? So this is our electrode, but then we say, and this is just all water here. If this is all water, and then I set the top to be 300 K, and then I set the bottom to be 300 K, and then I'm doing a bunch of heating here due to joule heating. Well, yes, your hot spot is going to be here, but then here is your cold right next to it. It's going to create an extremely high, an artificially high temperature gradient. And this is going to create your simulated electrothermal flow is going to be a lot higher because you've set the boundary condition too close. So that's why you need, one of the primary reasons why when you're modeling the temperature, you need to make sure that it is the whole system is modeled. And then you can just model in the liquid space, that is your electric field, and your fluid dynamic field. All right, so with the numerical simulations, we talked about the importance of modeling the whole space. And then we've also mentioned, so it's going to emphasize here, is that it can be decoupled. So just to review, what decoupled means is that you first solve for the electric field, and then after you solve for the electric field, the second step is that you solve for the temperature field, and then you solve the fluid dynamics. And it solves one to the next to the next. Now, what are some constraints on this? It assumes that all of your properties are constant. What do we mean by that? So technically, for example, the conductivity of your fluid might change with temperature, or viscosity. Viscosity might change with temperature. Now, this is fine if you're at low temperatures. Low temperatures meaning some authors say less than 5 degrees, some authors say less than 10 degrees. I would say definitely if it's more than 10 degrees, you should have a coupled system instead. But yeah, if you're less than 5, you can assume a decoupled system. But really with computation power nowadays, you can probably be coupled, especially for a 2D system, and it doesn't matter. What coupled means is that all three of these systems are solved simultaneously. So when they are solved simultaneously, then the information of one can get fed into the other. And then you can also potentially put in properties such as viscosity as an example, where its properties can change with temperature just for a little bit more accurate model. But we're saying it'll be a few percentages of error depending on your temperature and other conditions. But that's the difference between a coupled and a decoupled system. Now, before we move on, I do have some additional comments. So your heating sources can be either internal or they can be external. Now, if they're internal, that means it's joule heating. Joule heating is the typical culprit. So in other words, your electric field, and go back to that temperature equation, is that it is dependent on the conductivity of the fluid as well as the electric field. Now, the conductivity of PBS is on the order of 2 Siemens per meter, whereas that of DI water is typically much less, depending on your DI water source, is less than 0.01 millisiemens per meter. So if you do an experiment in DI water and things look fine, and maybe there's no electrothermal fluid flow, and then you're ready to put in cell growth media, well, you're going to heat your sample 20,000 times greater than what it was before. And you're also going to have that much greater electrothermal fluid motion. So joule heating is proportional to that. So that also means that if you double your voltage, you double your heating. So that is your heating source. Now, with respect to external, it could be illumination. So in some of our experiments, we used a laser to heat our system, and that produces, and that's an external source of heating. So in other words, our electric field does not heat our system, or at least you could have both simultaneously. You could, but you can have external illumination as your heating source. And there's a few publications on that. So we've talked about the heating relationship, but then with respect to the velocity relationship, now you also know that the electrothermal fluid body force is proportional to the electric field squared, but it's also proportional to temperature gradients. And that temperature gradients really, however much you're heating it, that's going to influence your electrothermal flow as well. So let's get back to it. Internal, external. Taking all this together, and I'm going to substitute voltage in instead of electric field. So if it's internal, your electrothermal fluid velocity is proportional to conductivity, voltage to the fourth, where if it's an external heating, it's conductivity, voltage to the second. So this means that if you double your voltage, yes, you will quadruple your heat, but you'll be at least a factor of 16 in terms of increasing your electrothermal fluid velocity. So that is one way that you can, why electrothermal flow can be exacerbated when you increase the voltage. Then it can be really fast compared to maybe some other aspects within your system. Now, if your heating is mostly external, it's proportional to conductivity and then voltage squared. All right, so let's go over an example. So the one on the top, we saw this before. So this is an example of internal heating. And the one on the bottom that I'll get to is an example of external heating. So in internal heating, they did, this is a simulation result that you can see from the paper below. And it modeled half the system. So remember that they modeled half of it. And this is the result that they got from their simulation. All right, that's fine. So this should be familiar. Now on the bottom, they did an experiment where they covered half of their system. So they let light hit the electrode, and then the electrode would catch that light and heat up. And the other side, they covered and made dark. And then they noticed the following fluid pattern based on the heating of the electrode. Now, technically, there is some internal heating going on as well because you're applying an electric field. But in this case, they say the significance, the significant portion of their heating was with the light interacting with the electrode, and then got some fluid motion there. So if you're using lasers or other high-intensity light and might be absorbed into your system and you're applying electric fields, be mindful that you might have illumination could influence what's going on with your system. All right, so what's next? How can you estimate, or what aspects could you estimate without doing numerical modeling? Now, the numerical modeling, in my opinion, is rather simple and straightforward, and that's what I recommend doing. But if some people would want to give an estimate of, say, for example, of the temperature that they use, they could say, okay, the temperature that they would expect, the temperature they would expect, that this would be a rough estimation based on the equations that we had before. But also notice that this equation doesn't take into effect the whole system, right? So maybe cover slips or silicon wafers or whatever it may be. But this is just a basic estimation if you want to figure out what your temperature was without numerical modeling. But the next aspect that I'm going to cover is that there are some papers, and some of them are referenced below at the bottom, where if they knew their expression of the electric field, so the example that I have here is that they estimated the electric field between two coplanar electrodes, and they ignored what was going on right at the gap. So they ignored that part. Again, there's assumptions that go on to here. If you're going to estimate it you're likely going to have to throw in some assumptions here, and the assumptions can potentially introduce error. Regardless, with the electric field, they estimated this as their analytical expression of their electric field, and if they did that, now that you have an analytical expression, now you can go through the mathematics and the calculations and figure out what it is. So, for example, the heat source, right? Remember that 1/2 conductivity electric field squared. If you wanted to calculate that, they use the electric field, they substituted that in, and then got their source. So this is their heat source based on this known electric field. So first you need an analytical expression to help you with this estimation, whether it be an assumed or an approximate analytical expression. You have an assumed temperature at the boundaries, either at the electrodes or nearby. So you have a simplified temperature field, or you have some heat transfer estimation. So what we did a publication a few years back where we looked at the resistance, the thermal resistance of our system, whether it be made of PDMS or silicon or whatever it may be, and we use that as our heat transfer estimation instead of a temperature, say, at the electrodes or something like that. But the details of these estimations, like I said, can be found in these articles. But if I were to do it, I would do numerical modeling for electrothermal fluid flow. So now let's get into, you have a numerical model or an estimation. What you need to measure this. You need to measure and quantify first temperature. Now, how do you go about doing this? So one way is to do a thermochromic liquid crystal. You can buy these encapsulated crystals that change their color with respect to the temperature that's applied to them. Now, this will give you an idea of the temperature, but it's not so great at measuring a temperature gradient because sometimes these crystals are just as large as the electrodes themselves. So you see 4 electrode fingers here for this system. So it can give you an idea of temperature, but not so much the gradients. Another thing you could do is that you can do particle tracking, and then from tracking you can look at the diffusion, also Brownian motion. You can look at the Brownian motion and random motion of the particles, and then from that you can deduce what the temperature is that they are suspended in. You could do that. We have the capabilities at our university to do microscopic infrared imaging. So you might be familiar with infrared imaging where you see a rainbow light color, say firefighters and other first responders or others have this capability, but that capability cannot just be applied to a microscope in a straightforward manner. It takes specialized equipment due to the features of the optical properties of infrared light interacting with features that are about the size of the wavelengths of that light. So there's a QFI infrascope that we use that can be used to measure temperature gradients of your system. And then you can also have an on-chip sensor, so maybe a thermistor or something like that could be incorporated within it as well. So all these are good. I like all of these, but the ones that I would prefer, now the QFI infrascope is really nice for us to have, but before we had this, the technique that I use that I find helpful is to use temperature-dependent dyes, also known as fluorothermometry, also known as laser-induced fluorescence. But what happens is that you have a dye, and then with that dye, once you apply an electric field, its fluorescent intensity will decrease. So in this case, we have an electrode strip here that you can see on the slide, and then here the same strip, same system, but now we've heated it up. And you could look at this and you might see the one on the right as a little bit more dim. That's good, but then you overlay them, you compare the pixels, and then you have that with a known calibration. So you do have to calibrate your dye as well with a known temperature, whether it be with a heat cell or something else. But either way, you need to calibrate your dye so then you can ultimately know what your resulting temperature is based on its how much it changes. And you typically do a ratio, so a ratio of your measured over your initial, and then you compare that with a calibration, and then you can get your temperature from that. So here is a reference for you to look at the technique that we did. Now, in this case, just be mindful, you're getting temperature gradients in these directions. So we'll just say the X direction and the Y direction for simplicity. So in other words, the temperature gradient in the Z direction, we can't determine that. Now, if you had a confocal system or a way to scan fluorescence in the Z direction, you might be able to get some insight into that. So, but for this technique, it's going to be lost here. And you could say the same for, say, the QFI infrascope as well, that infrared microscope. It's going to be a depth average system. So that is a little bit more challenging to measure. So with that, that's where numerical simulations can be valuable. And then here is a result from that study. Let me get what I was writing out of the way. So here we looked at heating when we have different fluid conductivities. And then we have the horizontal axis is the square of the applied voltage. And we looked at how much did our system heat up? What was the temperature of our system? So then we had our different simulation points. Different measurement points, and then we had simulations in the straight lines. So it was rather close. All right. Now, what about measuring the electrothermal fluid flow itself? So measuring the electrothermal fluid flow itself, they're really microfluidic flows when there's particles present. You're going to do PIV, either particle image velocimetry or particle tracking velocimetry. Particle image velocimetry is shown here on the right. And here in this study, we look at electrothermal flow. And it's typically 2D because you're looking at typically a camera image or a series of images and frames. And then from that, you can track what the electrothermal fluid velocity is in this case, at least in this plane. Now, if you wanted to figure out what the electrothermal fluid flow is in 3 dimensions, then you would do some particle tracking velocimetry. So you would track individual particles. There's a variety of methods of doing that, especially under a microscopic system. One of the easiest ways is to put a cylindrical lens in front of it. And that uses just a cylindrical lens and a single camera, and you do have to calibrate the particles that you're using against a library. But there's also emerging techniques, whether you use artificial intelligence, whether it be using other optical approaches. So this is an expanding area. But either way, 3D tracking, a 3D particle tracking is a way to measure fluid velocity in that way. So what sometimes I'm asked is that we have electrothermal flow. How do we reduce it, right? How can we have less of this fluid motion because maybe I don't want it? Sometimes you do want it. Sometimes it's fine. Maybe if you're trapping particles, it helps bring particles in closer to the trapping region. Sometimes you don't want it at all. Now, the easiest one is, well, okay, change your voltage and change your fluid conductivity. The fluid conductivity might be easy. They do make low conductivity growth media if you are using biological samples. You can do that. But then also reducing voltage. You might say, well, of course, I can reduce voltage. But think about it. It's to the 4th power. So even if you reduce it just a little bit, that may help you. Another thing is to reduce the temperature gradient. Now, how could you potentially do that? Well, you can reduce the temperature gradient by also changing the overall temperature. And one way of doing that is maybe you want to have a silicon substrate instead of a glass substrate. That can transfer your heat out a little bit more. So that's one example. But then also we have to think about the dot product itself. So if you have a system where your temperature gradient is one way and your electric field is another way, then that's going to be a very strong electrothermal system. Where instead, maybe if you can, even if you can slightly change your system, whether it be through a design or something else, if the majority of your electric field is now in a different direction, now you're going to have less electrothermal hydrodynamics than you did for the other system. Now, sometimes this is unavoidable, right? So this is something that should be that you should consider if you can design this or get this out of your system. And then the other aspect is you can just have a smaller fluid volume. You're heating less. So if you have a system, let's say you have an electrode system. So I have an electrode here, and I have a certain channel height associated with this. Well, just decrease, if you're able to, decrease your channel height. And if you do that, you're heating less. You can think of it as that you're not as much volume is being heated by your electric field. Now, when you do that, you might decrease your throughput of your system, and you may not want that. But either way, this is a potential way of reducing electrothermal fluid flow. All right, so that wraps up my talk here on electrothermal fluid motion. If you have questions, feel free to contact me. We have some of the publications that we've talked about, at least from my lab, are on our website at microfluidics.louisville.edu. Some of our videos are on our YouTube page at UL Microfluidics. I did reference a lot from the Morgan and Green book, and some of Green's papers are also within that as well. So that's a good source for electrothermal fluid flow. And then also dialectophoresis, Dr. Petheg's work is good as well. So with that, I will end this video, and feel free to reach out if you have any questions.